There is a place in the Atlantic Ocean where ships vanish without sending distress signals, where entire squadrons of military aircraft disappear from radar screens and are never seen again, where rescue teams searching for missing vessels themselves go missing, adding to a list of unexplained losses that spans over a century. The Bermuda Triangle. Just hearing the name conjures images of mysterious forces, supernatural disappearances, and waters that swallow everything that crosses them. But what actually lies beneath these waters? What geological features exist at the bottom of this infamous region? And is there something about the ocean floor itself that could explain why so many ships and planes have met their end here? Let's descend beneath the surface and explore the actual depths of the Bermuda Triangle. Because what we find down there is strange enough without needing supernatural explanations. The Bermuda Triangle covers approximately 500,000 square miles of ocean between Miami, Bermuda, and Puerto Rico. That's an area larger than the combined size of Texas and Louisiana. Within this vast region, the ocean depth varies dramatically, creating underwater terrain more complex than almost anywhere else in the Atlantic. At the surface, the water looks ordinary, blue, sometimes green near the shallower banks, occasionally glowing with bioluminescence at night. Ships crossing these waters see nothing unusual. The ocean appears calm, unremarkable, just another stretch of the Atlantic. But beneath the surface, the seafloor tells a different story. At 50 meters depth, we're still over the Florida platform, the shallow limestone shelf extending from the Florida coast. The water here is relatively warm, filled with marine life, popular with divers who explore shipwrecks and coral formations. This is where recreational boats spend most of their time, fishing, diving, cruising through waters that seem completely safe. At 100 meters, we pass over the edge of the Bahamas banks. These are massive shallow platforms rising from the deep ocean floor, covered in white carbonate sand that makes the water above them glow turquoise. The banks drop off suddenly, creating underwater cliffs that plunge from sunlit shallows into darkness within just a few hundred meters. At 200 meters, we cross into the twilight zone. Light is fading. The warm surface waters give way to the thermocline, a sharp temperature boundary where the ocean suddenly becomes much colder. This is where submarines hide, using the temperature layers to confuse sonar. This is where large predators hunt, and where the ocean starts to reveal its hidden complexity. At 500 meters, we're descending through one of the complex current systems that makes the Bermuda Triangle so dangerous to navigation. The Gulf Stream, one of the strongest ocean currents on Earth, flows through this region at speeds up to 5 miles per hour. That might not sound fast, but for ships and aircraft, it's enough to push them significantly off course without anyone noticing until it's too late. At 800 meters, we reach the depth where submarines operate. Down here in the darkness, naval vessels move silently through water that's just above freezing. This is also the depth where many deep-water fishing vessels work, their lines extending down into the darkness searching for tuna, swordfish, and other large predators. At 1,000 meters, we're now in complete darkness. No sunlight has reached this depth for millions of years. The pressure is 100 times what it is at the surface, enough to crush an empty oil drum into the size of a coffee can. The temperature hovers around 4 degrees Celsius, cold enough that without thermal insulation, a human body would develop hypothermia in minutes. At 1,500 kilometers long and up to 120 kilometers wide, the Puerto Rico Trench cuts across the southern edge of the Bermuda Triangle region. This is the deepest trench in the Atlantic Ocean, a massive underwater canyon where the ocean floor drops to depths that challenge human understanding of what the deep sea looks like. At 2,000 meters, we're descending into the Puerto Rico Trench. The walls of the trench are steep, dropping at angles that would be considered extreme mountains if they existed on land. These underwater cliffs are covered in sediment, layers of mud and volcanic ash that have accumulated over millions of years. At 3,000 meters, we pass the depth where the Titanic rests, though that wreck lies far to the north, outside the triangle. But at this depth in the Puerto Rico Trench, the conditions are similar: cold, dark, under crushing pressure. Any ship that sinks to this depth would be preserved in the near-freezing water, its metal slowly corroding, its structure gradually collapsing under the weight of water above it. At 4,000 meters, We're now in the abyssal zone of the Puerto Rico Trench. The seafloor here is covered in fine sediment, a mixture of volcanic ash from underwater eruptions, microscopic shells of dead plankton that rain down from the surface, and clay particles carried by deep ocean currents. The sediment accumulates slowly, about 6 millimeters every 150 years. At 5,000 meters, we begin to encounter something unusual. Strange mounds in the sediment, irregular bumps in what should be a flat abyssal plain. These are methane hydrate deposits, frozen concentrations of methane gas trapped in ice like structures on the seafloor. Methane hydrates exist in many deep ocean locations, but the concentrations in the Puerto Rico Trench and near Blake Ridge off the southeastern U.S. coast are particularly large. Some estimates suggest there could be more energy trapped in these methane deposits than in all of Earth's known oil and gas reserves combined. But methane hydrates are unstable. If the temperature rises or the pressure decreases, they can suddenly release massive amounts of gas into the water. And this is where things get interesting for explaining some Bermuda Triangle disappearances. At 6,000 meters, we're deep in the Puerto Rico Trench now, approaching some of the deepest waters in the Atlantic. The pressure here exceeds 600 atmospheres, over 8,800 pounds per square inch. The darkness is absolute. The only lights visible are the bioluminescent flashes of deep sea creatures, rare and scattered in the vast emptiness. At 7,000 meters, we're nearing the maximum depth of most of the Puerto Rico Trench. At this depth, the ocean floor is covered in what scientists call pelagic clay, the finest sediment imaginable, particles so small they take decades to settle from the surface. This clay is mixed with volcanic ash from ancient eruptions and the occasional meteorite fragment that survived entry through Earth's atmosphere. At 8,000 meters, we reach areas that have only been explored a handful of times. The first detailed surveys of the Puerto Rico Trench didn't happen until the 1960s, and even today, most of this region has never been directly observed by humans. What we know comes from sonar mapping, from remotely operated vehicles, from scientific instruments lowered on cables from ships at the surface. At 8,380 meters, we reach the Milwaukee Deep, the deepest point in the entire Atlantic Ocean. This spot, located within the Puerto Rico Trench, is deeper than Mount Everest is tall. If you could somehow transport the world's highest mountain and drop it into the Milwaukee Deep, the summit would still be over 2,000 meters underwater. This is the deepest point in the Bermuda Triangle region. And despite all the mythology and speculation, there's nothing supernatural at the bottom. Just cold, dark water. Sediment. Deep sea organisms adapted to crushing pressure. The same abyssal environment found in deep trenches worldwide. But there is something unusual about this region that doesn't require supernatural explanations. The geological structure of the Bermuda Triangle is genuinely complex in ways that make it more dangerous than most other ocean areas. The seafloor here contains features rarely found together in such a small region. Shallow banks that rise to within meters of the surface. Deep straits between islands where currents accelerate to dangerous speeds. Underwater mountains and seamounts scattered across the deep plain. And the Puerto Rico Trench cutting across the southern boundary like a scar in the Earth's crust. The northern part of the Bermuda Triangle sits on the Bermuda Plateau, a relatively flat raised area of seafloor. But this plateau is dotted with underwater mountains, conical peaks that rise 150 to 200 meters from the surrounding plain. These seamounts are arranged in clusters, some named, most anonymous, mapped but never visited. The Bermuda Islands themselves are the peaks of the largest seamounts, breaking the surface to form the only substantial land in this vast stretch of ocean. But Bermuda is unusual. It's not a typical volcanic island. It formed through a process that geologists didn't fully understand until recently. In 2019, researchers analyzing an 800-meter deep core sample drilled in 1972 discovered something strange. The mineral composition and lead isotopes didn't match what you'd expect from normal volcanic activity. The rock contained fragments that appeared to come from ancient tectonic plates that had sunk deep into Earth's mantle hundreds of millions of years ago. The theory now is that disturbances in the mantle caused these ancient plate fragments to rise back up, mixing with molten material, interacting with seawater, and eventually erupting to form Bermuda around 30 million years ago. This type of volcanic formation was unknown before studying Bermuda, and it may explain how other isolated volcanic islands formed around the world. But the most intriguing geological feature isn't the seamounts or the plateau. It's what lies beneath everything else. The limestone platform. The Bermuda Triangle sits on a limestone base that's nearly 6 kilometers thick. 6 kilometers of limestone, all formed from the accumulated shells and skeletons of tiny marine organisms that lived and died in these waters over hundreds of millions of years. This limestone platform is one of the thickest carbonate deposits anywhere on Earth. It formed because this region has remained geologically stable for an extraordinarily long time. While other parts of the ocean floor were being created, destroyed, subducted beneath continents, folded into mountains, this area stayed relatively calm, allowing limestone to accumulate layer after layer. And within this limestone are caves, underwater cave systems that extend for kilometers, some connected to the surface through blue holes, vertical shafts that drop suddenly from shallow water into darkness. These caves create complex water circulation patterns, affecting currents, creating whirlpools and eddies that can be dangerous to small vessels. The southern part of the Bermuda Triangle is even more complex. The Florida platform meets the Bahamas banks, creating a maze of shallow areas interrupted by deep straits. The Straits of Florida, where the Gulf Stream accelerates as it squeezes between Florida and Cuba, creates currents strong enough to push ships off course or overwhelm small boats. And then there are the ocean currents themselves. The Gulf Stream flows through the Bermuda Triangle at speeds up to 5 miles per hour, carrying warm water from the Caribbean northward along the U.S. coast. But the Gulf Stream doesn't flow smoothly. It creates eddies, meanders, rings of rotating water that can be 100 kilometers across. These eddies can trap ships, carrying them in circles, pushing them off their intended course by dozens or even hundreds of miles. Before GPS, before modern navigation, ships entering an eddy might not realize they were off course until they were hopelessly lost. Aircraft flying at low altitude could be affected by the winds that eddies create, pushed off course just enough that their navigation calculations became useless. The atmospheric conditions above the Bermuda Triangle are also unusual. The region sits where cold air masses from the north meet warm tropical air from the south. This creates instability, sudden storms, waterspouts, and weather patterns that can change from calm to dangerous within minutes. Waterspouts, tornadoes that form over water, are common in the Bermuda Triangle. They can appear with little warning, generating winds over 100 miles per hour in a column sometimes barely 50 feet wide. A ship caught in a waterspout could be damaged or sunk before anyone on board realized what was happening. And then there are rogue waves. These are freak waves that appear suddenly in otherwise calm seas. Walls of water 80 feet tall or more, generated by the interaction of multiple wave systems or by the focusing effect of underwater terrain. Rogue waves have sunk large ships, damaged oil platforms, and been recorded by sensors all over the world's oceans. In the Bermuda Triangle, with its complex seafloor topography and strong currents, rogue waves are more likely than in many other areas. A ship encountering a rogue wave in the middle of the night with no warning might sink in seconds, sending out no distress signal, leaving no survivors. But let's return to those methane hydrates at 5,000 meters depth, because this might be the most scientifically plausible explanation for some of the triangle's mysterious disappearances. Methane hydrates are stable only under specific conditions of pressure and temperature. If something disturbs them, an underwater landslide, an earthquake, a change in water temperature, they can suddenly decompose, releasing huge amounts of methane gas. This gas rises through the water column in massive bubbles. And here's the critical part. Water filled with gas bubbles loses density. A ship floating in normal seawater has buoyancy because water is denser than the ship's average density. But if the water suddenly fills with gas, its density drops dramatically. Experiments with ship models have demonstrated this effect. When researchers created artificial gas eruptions beneath floating models, the models sank rapidly, pulled down by their own weight in water that was no longer dense enough to support them. A ship caught in a sudden methane eruption would sink before the crew could react. No time to send a distress signal, no time to launch lifeboats. The ship would just drop, pulled down into water that had temporarily lost its ability to provide buoyancy, sinking to the seafloor thousands of meters below. And once the methane dispersed, the water would return to normal density, leaving no trace that anything unusual had happened. No debris field, no oil slick, nothing to indicate a ship had just vanished. Aircraft could also be affected. A large methane release could create a column of gas rising through the atmosphere. An aircraft flying through this column would experience a sudden loss of engine power, as the methane displaced oxygen, potentially causing the engines to flame out. The aircraft would drop from the sky, crashing into the ocean with no survivors. But here's the important caveat. According to the U.S. Geological Survey, there's no evidence of major methane gas releases in the Bermuda Triangle region in the past 15,000 years. The methane hydrates are there, certainly. They exist in large quantities, but they've remained stable. So while methane eruptions could theoretically explain some disappearances, there's no direct evidence they've actually occurred in modern times. Most Bermuda Triangle disappearances have more mundane explanations. Storms, navigational errors, mechanical failures, human mistakes, rogue waves, strong currents. The same things that cause ships and aircraft to vanish in other parts of the world's oceans. The difference is that the Bermuda Triangle has a reputation. When a ship disappears here, it makes headlines. When a ship disappears elsewhere, it's just another maritime accident. Sad but unremarkable. Statistical analyses have shown that the Bermuda Triangle doesn't have a higher rate of disappearances than other heavily trafficked ocean regions of comparable size. The number of incidents is consistent with what you'd expect, given the amount of ship and aircraft traffic passing through. But the reputation persists, because humans are drawn to mystery, to the idea that some places on Earth hold secrets we haven't uncovered, dangers we can't explain. And beneath the Bermuda Triangle, in the Milwaukee Deep at 8,380 meters, in the darkness and crushing pressure, there are certainly secrets, shipwrecks we've never found, aircraft that disappeared decades ago, their wreckage scattered across the abyssal plain, evidence of incidents that we've only guessed at from the absence of vessels that never returned. The Bermuda Triangle is mysterious not because of supernatural forces, but because the ocean itself is mysterious. Because even in regions we've studied extensively, we've barely explored the depths. Because the seafloor remains one of the least known environments on Earth. We've mapped the surface of Mars in higher resolution than we've mapped most of the ocean floor. We've sent more people to space than to the deepest parts of the Bermuda Triangle. The Milwaukee Deep has been visited by remotely operated vehicles only a handful of times. So when we ask what lies beneath the Bermuda Triangle, the honest answer is, we don't know everything. We know the major features: the Puerto Rico Trench, the limestone platform, the seamounts, the methane hydrate deposits, the complex currents and the unusual atmospheric conditions. But we don't know every detail. We don't know the location of every shipwreck, every downed aircraft, every piece of evidence that could help explain the disappearances that built the Triangle's reputation. What we do know is that the geology is complex enough, the current strong enough, the weather unstable enough, that this region deserves its reputation as challenging to navigate, even if that reputation has been exaggerated into something supernatural. The Bermuda Triangle isn't cursed. It's just a difficult patch of ocean, with deep trenches, strong currents, sudden storms, and geological features that make it more dangerous than average. Combined with heavy ship and aircraft traffic over decades, that's enough to create a list of disappearances that seems suspicious when you ignore the context. But context matters. And when you descend beneath the surface, when you explore the actual depths, when you understand the geological forces that shape this region, the mystery becomes less about supernatural forces and more about the raw power of the ocean itself. The journey to the most mysterious depths of the Atlantic ends at 8,380 meters in the Milwaukee Deep, at the bottom of a trench that cuts through one of the most heavily trafficked regions of the world's oceans. In darkness that has been absolute for millions of years. In water cold enough to preserve anything that sinks here almost indefinitely. And somewhere down there, scattered across the sediment, lie the answers to some of the Bermuda Triangle's mysteries. Shipwrecks we've never found, aircraft fragments we've never recovered, evidence that would turn supernatural speculation into mundane explanation. But until we explore these depths more thoroughly, Until we map every meter of seafloor and investigate every anomaly, the Bermuda Triangle will keep its reputation. Not because it's genuinely more dangerous than it should be, but because humans need mysteries, need places that challenge our understanding, need regions of the ocean that still hold secrets. And beneath the Bermuda Triangle, 8,380 meters down in the Milwaukee Deep, those secrets remain, waiting in the darkness. Preserved in water that's just above freezing, hidden in sediment that accumulates at 6 millimeters per century. The Bermuda Triangle's deepest depths aren't supernatural, but they're mysterious enough.